Alright, hello everyone. So if you are here, that means you missed some questions about chemical reactions and applications on the practice test. So this is a good place to be because we're just going to go over a lot of information about chemical reactions and then go into specifics about acids and bases, nuclear, organic, and let's see what else, redox. Alright, so we'll start with just types of chemical reactions. So there's 4 types of chemical reactions that you are responsible for memorizing and being able to recognize on the chemistry regions. So what we're going to do is just go through and using letters as examples of reactants and products. So we're not going to write an actual synthesis, decomposition, single and double replacement reactions, but you'll get the idea for what these look like. So synthesis reactions, that's when you take 2 products and you combine them together to just, 2 reactants, and you combine them together to just create 1 product. So that's a synthesis reaction. Decomposition is just the opposite of a synthesis. That's when you're breaking down 1 reactant into its component parts. Single replacement looks like this, or at least this is a model of a single replacement reaction. So notice that at first the A was by itself, B and C were joined together, and then we had a little flip-flop, single replacement. Double replacement we can represent as follows, and make sure you are taking notes on your paper as well. So you can see in the double replacement reactions, we've got A and B and then C and D together, but then they both kind of flip-flop who they're with. So now A is matched up with D and C and B are matched up together. So being able to recognize those reactions is going to be crucial for getting points on the Regents. So make sure you do the practice questions that should be popping up in the video right about now. Hope you did alright with those practice questions. Now we're going to move on to acids and bases. So just a general overview of acids and bases. Don't forget, acids are located on table K of your reference tables, which you should have handy. So we can just show that real quick. Table A, common acids, and then your bases are going to be found right below it on table L. So how are acids and bases defined? Well, you can gather this information really by just looking at the different examples. So for instance, acids, all of them have this hydrogen at the start of their formula, right? So acids, when they're dissolved in water, will release or donate, or if you see the word yield, just know that it means donate or release. They're going to yield that hydrogen ion in solution. All right, and you might see its name, the hydronium ion. So what about bases? What do they do? Well, let's look at them. Bases, we'll talk about why ammonia is listed here. But all 3 of these bases all have this OH ion, the hydroxide. So when bases are dissolved in water, they will release or donate or yield. Any one of those words means the same thing. The OH minus or the hydroxide ion. And I just realized it went off screen. Sorry about that. Let's zoom out. So there's our definitions of acids and bases according to Arrhenius. So if you see that word, don't let it scare you, that's just the name of the scientist who developed this theory, this understanding of acids and bases and how they behave when they dissolve in water. The alternate theory matches this for the acids. They're known as H+ donors. And then bases are known as H+ acceptors, which is why NH3 is listed as a base. NH3 has a lone pair of electrons on the nitrogen, and that's going to attract an H+, so that process of accepting an H+ makes ammonia a base. Alright, keep in mind both acids and bases are electrolytes. So if you're asked to identify an electrolyte, you can always go to table K or table L to see if one of the options is listed on there, because you know if it is, then that's an electrolyte. Acids have a pH less than 7, bases have a pH greater than 7. We'll look more carefully at the pH scale in a moment. But before we do so, let's talk about the types of reactions involved for acids and bases. And those are called neutralization reactions. So here's the general reaction. If you react an acid and a base, you're going to get two products every time. One of those products is always water, and the other product is a salt. All right, and a salt is just an ionic compound. So we'll do an example. Here's my acid, HCl. If I react that with sodium hydroxide, NaOH, what's going to happen is the acid's going to donate the H+, the base is going to donate the OH-, and these two can combine to create water. And then what's left over is going to combine to create a salt. All right, in this case, sodium chloride. When that happens, now you've got your pH back to 7. All right, it's neutral. And that's a nice lead-in into the pH scale. So right in the middle of the pH scale, that 7 means neutral. So in terms of these important ions, the H pluses and the OH minuses, at a pH of 7, they are equal. Lower pHs, as we talked about before, are acids. All right, and since acids donate the H+, there's going to be a lot more H+ ions than the OH- at these lower pHs. And then on the other side, we've got our bases. And since bases donate the OH-, there's going to be a lot more OH- than H+ at these higher pHs. One more thing before we move on, just keep in mind the relationship between pH and the concentration of this H+ ion. So every jump down the pH scale actually represents a 10 times increase in that concentration. So those brackets mean concentration. So one jump down the pH scale means a 10 times increase in the concentration of H+. Be sure you know how to answer those questions. Hopefully you'll see an example popping up in the video right about now. All right, moving on to reduction and oxidation, so redox reactions. What's going on there? Well, in a redox reaction, electrons are transferred. They're transferred from one species to another, resulting in changes in oxidation number. Recall that oxidation number is just the charge of a species, the charge of an ion, and you can find those oxidation numbers on our periodic table. Those are the numbers in the upper right-hand corner for each element. So how do we identify redox reactions? By looking for changes in charge, changes in oxidation number. So if I've got a reaction and I need to determine is this redox, I've got to first assign those oxidation numbers. Elements that are just by themselves, those are neutral atoms, so they do not have a charge. So they're assigned a number 0. This guy, silver nitrate. Well, if I look at Ag on my periodic table, it only has one possible charge when it's combined with another element, and that's +1. So this must be +1. All right, and I'm actually not going to worry about defining the oxidation number states for the NO3 just because it shows up on both sides of the equation, so its charge won't be changing. So we'll just move on to the silver atom as a product. So this is a neutral atom. its charge is 0. And then zinc. Well, if I look at zinc on my periodic table, it only has one possible oxidation number, and that's +2. So what happened here? Is this a redox reaction? Yes. How do we know? Well, the charge of the neutral zinc atom that we started with, this species, goes up to zinc 2+. Meanwhile, the charge of the silver ion, the Ag+1 that we started with, goes down to just a neutral silver atom. So because we have these changes in oxidation numbers, this has to be a redox reaction. There was some sort of transfer of electrons involved. So let's look at that transfer of electrons a little bit closer by using these words reduction and oxidation. And keep in mind, we have a couple ways to remember this. Leo the lion says gur, and oil rig. So Leo, losing electrons, is oxidation. So let's add that here. Leo the lion says gur, gaining electrons, is reduction. Let's add in our notes here what happens to charge. So when you gain a negative electron, you become more negative. Your charge goes down. Meanwhile, if you lose a negative electron, you become more positive, so your charge goes up. And we can write half reactions for these processes. So we will use the same example up here, and we're just going to focus on the species that are undergoing this change in charge, and we're going to look at them separately in a half reaction. And a half reaction is going to show the change in charge, but it's also going to show how the electrons were involved. All right? So let's start with the reduction. Gaining electrons, charge goes down. So that's what happened with my silver ion. I started with this silver ion. It ended up as a silver atom because it gained electrons. Well, how many electrons did it gain? To go from 1 down to 0, it must have just gained 1 electron. And you include that on the side with the charged particle, gaining electrons. Meanwhile, losing electrons, well, that was my zinc atom. Its charge went up, it became oxidized. So how do I show that? It started off as the neutral zinc atom. It ended as the zinc 2+ ion. How did that happen? It lost electrons. I include the electrons on the side with the charge. How many do I include in this case? 2. 2 electrons were lost in this process. All right? Here's the thing about redox reactions, though. The number of electrons lost equals the number of electrons gained. All right? In order to have a balanced redox reaction, this has to be true. So right now, as written, this reaction is not balanced, because when I looked at my half reactions, the silver ion is gaining 1 electron, but the zinc atom lost 2. So how can I fix this? How could I balance this and then add them up together to get my net ionic equation? Well, I want to make sure the electrons are the same. So I can manipulate this half reaction by multiplying everything by 2. And that way, that will transfer to the number of electrons. 2 electrons gained will equal those 2 electrons being lost. So the net ionic equation then is going to show all of my reactants added up together, and then all of my products added up together. So my reactants, now I've got 2 silver ions. I've got 2 electrons. But I'm also adding this half reaction, so I'm going to add a zinc atom. Now I can look at my product side. I've got 2 silver atoms. And then what's left over here? The zinc ion and then 2 more electrons. Now that the electrons are the same on both sides, I can go ahead and cross those out. And what's left is my net ionic equation. Electrochemical cells are an application of redox reactions. And there's 2 types of electrochemical cells. There's voltaic and electrolytic. In both cases, we can use this phrase to help remember what's going on. An ox and a big red cat. NOx, what does that mean? It means oxidation happens at the anode. Big red cat means reduction happens at the other electrode, which is called the cathode. Alright, and it's big because, as you're going to see in our example, the mass of the cathode increases. Alright, so let's look at voltaic and electrolytic. Let's identify their differences, their similarities, and then we can move on to nuclear. So a voltaic cell works by spontaneously converting chemical energy into electrical. On the other hand, an electrolytic cell is non-spontaneous. So in other words, it's trying to generate some chemical change, but the chemical change is non-spontaneous. It's not going to happen on its own. So because of that, electrolytic cells always need a battery, a power source. And what it does with that power source is it takes that electrical energy and uses it to create a chemical change. So why would we want to do this? Well, an application would be for electroplating. Oops, sorry, I went off screen. Alright, so in electroplating, we can take a metal and actually coat it to the outside of a different metal. We can do this to create cheaper jewelry. That's one example. And notice this is a nice diagram. It labels which electrode is the anode. So the anode is where oxidation occurs, right? So oxidation loses electrons. These electrons are being pulled away by the battery. The battery is pulling those electrons away, forcing the nickel to oxidize. And then meanwhile at the cathode, the electrons are being gained, and therefore the nickel ions that were in this solution, when they gain those electrons, they will plate onto the cathode. In a voltaic cell, now you have a spontaneous chemical change. So what do I mean by that? Well, copper and silver. If you compare the reactivities of those metals, so on table J, if you compare copper and silver, copper is more active than silver. It's higher up. So metals that are more active want to lose electrons. They want to become oxidized. So the copper electrode here is the anode. It's spontaneously going to lose electrons. They're going to travel through this wire over to the silver cathode, where they're going to be gained by those silver ions in solution. So ions are turning into atoms, and these atoms can stick to that cathode and increase its mass. All right, big red cat. Meanwhile, at the anode, electrons are being lost, so you've got atoms turning into ions. And these ions can break away, float off into solution, and therefore the mass of the anode actually decreases as the cell operates. And what about the salt bridge? Well, the salt bridge allows for the flow of ions. All right, and that is necessary for this to work. or else there would be a charge buildup and it would halt the flow of this battery. That's what a voltaic cell is. It's a battery. I've got one set up here with copper and silver. Alright, so you can see here are my two electrodes. Here's the salt bridge. So what goes through the salt bridge? The ions. And you can actually see the copper ions that have been migrating through the salt bridge. They're blue. And as they migrate over, you can actually see them migrate. So if you've ever second guessed that ions go through the salt bridge, now you know. Alright, and I've got a voltmeter hooked up. You can see that it is in fact conducting electricity. The electrons are going from the anode to the cathode. Remember that little annoying song? I will not sing that for you, but you can look that up on YouTube if you want some extra help. Alright, where are we at? I think organic chemistry, right? That's the next one in your packet. So for organic chemistry, ultimately you've got to know how to use table P, table Q, and table R. So you will see in this video there's plenty of practice problems to make sure you understand how to use those tables. We're going to just do some important definitions in this video. So isomers have the same molecular formula but different structural formula. So as an example, we'll draw the isomers of C4H10. C4H10 matches up on table Q with this homologous series. That's the alkane. So it's all single bonds. So I've got 4 carbons, 10 H's. If I were to name this, according to table P, 4 carbons gets a prefix of bute. According to table Q, it's an alkane, so it gets the ANE ending. So that's one isomer. What's another isomer of C4H10? Well, what if instead of having 4 carbons in a row, I only had 3 carbons in a row, and then I added in the 4th one to this middle carbon? If I go to add my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'll see that it's got that same molecular formula, but now it has a different structure. Alright? It's got a different name. We're going to name this guy based off of its longest chain, which is only 3 carbons. So its foundation is going to be propane. And then what do I do about this branch? Well, I name it according to how long it is. It's only got 1 carbon, so it's methyl. Lastly, I put the number. It's coming off of the 2nd carbon in this long chain. So 2 different molecules here. They're going to have different properties. Different structural formula means they're going to have different properties, but they do have the same molecular formula. Another thing, make sure you remember what an empirical formula is. So that's just taking the molecular formula and reducing it to the smallest whole number coefficients by dividing by the greatest common factor. So C4H10, both of those numbers, 4 and 10, are divisible by 2. So the empirical formula would be C2H5. All right. Organic reaction types, there's 7 that ultimately you just got to memorize. This example, you see what's happening from left to right. We are replacing or substituting one of these H's with a chlorine, right? So this is a substitution. When you have a situation like the second one here where you start with an alkene, all right, that double bond, and you add 2 more atoms so that you turn that alkene into an alkane, that is called addition. The next example, when you've got a hydrocarbon, so just carbon and hydrogen, you burn it in the presence of oxygen to create carbon dioxide and water. That's combustion. These are highly exothermic reactions. Energy is also a product. This next one, we have to look at the functional groups of the molecules we're dealing with. So table R is where you would go to find that out. Table R, that tells you that's an organic acid. This is an alcohol. And what are we creating? Well, that's an ester. Directly off of table R, you can figure that out. What you're going to have to memorize is that the process of creating an ester is called esterification. All right, polymerization, making big molecules, which are called polymers, out of the same small unit, monomer. So make sure you memorize that. Fermentation, the process of creating beer. So keep that in mind when you're thinking of the products of fermentation. One of them is alcohol, and the other one is carbon dioxide. All right, beer is bubbly, but you should not know that until you're 21. Saponification, makes soap. That's all you have to know for that. Sapo, soap. All right, finally, nuclear chemistry. Just like with organic, there's important reference tables that you've just got to know how to use, reference table N and O. I want to go through some definitions with you. Transmutation, a change in the nucleus that converts it from one element to another. Transmutation, the change from one element to another. This can happen naturally. So for instance, if I looked at table N, that's got a whole list of nuclides or isotopes that are unstable, which means they are naturally going to decay on their own. And when that happens, you'll see there's been a change that converts it into a different element. So let's look at iodine 131 as an example. Iodine is atomic number 53. If I look at table N, iodine 131 undergoes beta decay. That's when you bring in table O to find that same symbol. That's how I know it's a beta decay, and I use this notation in my equation here. So this iodine 131 is radioactive, it's unstable, it will spontaneously emit this beta particle. And what am I left with then? Well, according to the conservation of mass, I need to make sure this number is the same, can add to 0 to equal what's on the other side. This number has to add to -1 to equal what's on the other side, so that has to be a 54. And if I look at the periodic table, I'll see that that is the element xenon. All right, so change in the nucleus, change in the element. This is natural. It's only got one reactant. Versus artificial, so an example of that would be like the fission of uranium-235, which you'll see in an example in the video. It'll pop up as a question. The fission of uranium-235 has two reactants. So it's an artificial transmutation. It doesn't happen on its own. It needs another particle to collide with it to get this process to take place. Half-life is defined as the rate of decay. And how you solve half-life problems can be different depending on what you like, but I like setting up the table. So time, half-life, and amount. How much time does it take for a 100-gram sample of iodine 131 to decay so that only 25 grams of this iodine remains unchanged? Well, we started off with 100 grams. That was at time 0, which means no half-lives have passed. I'm trying to figure out how much time it takes for that 100 grams to break down to 25. And each half-life is going to break this down in 1/2. So 100 divided by 2. And then 50 divided by 2 gets me to that 25. All right, 25 grams is where I know to stop. That took 2 half-lives. How long, though? I'm looking for the actual time. How much time does this process take? If I go back to table N, the half-life of all these isotopes is given to you. So iodine-131, it takes about 8 days for half of it to decay. So after 1 half-life, 8 days have passed. After 2 half-lives, I just add the half-life again. So 16 days. Alright, just like in organic where there were 7 reaction types to memorize, you've got 5 radioisotopes that you need to memorize for the Regents exam. So we're just going to go through these quickly. Used for dating of geological formations, that's uranium-238. Used for dating once living organisms is carbon-14. Used for detecting thyroid disorders, that's iodine-131. That's got a fairly short half-life of only 8 days, so that's why we can use it in the medical industry. It can be quickly eliminated from our body. Cobalt-60 is used for treating cancer, and then technetium-99 is used for detecting cancerous tumors. All right, they also have short half-lives, so they can be relatively quickly eliminated from the body. On the other hand, uranium has a half-life of 4.5 billion years. That's why we can use it to date these older geological formations, the age of the Earth, the rocks. All right, last little bit of this video here is about equilibrium. So equilibrium means what? Equal exchange. So the rates of the forward and the reverse reaction are occurring at the same rate, so that you have constant concentration. But what would happen if you disrupted that equilibrium? You applied some sort of stress. Well, the system, according to Le Chatelier, is going to respond by shifting left or right. So we'll go through 5 examples here. If I increase the concentration of A, I'm increasing the concentration of A, the system is going to respond by shifting away. It's going to shift to the right. If I decrease the concentration of B, decrease one of my reactants, the system is going to respond by producing more of what we just lost, so it's going to shift to the left. Increasing temperature, well, this is an exothermic reaction. Heat is a product, so you can think about temperature being a product. If I add more of this product, it's going to shift left, away from that stress. Decrease the pressure. Well, these are all gas particles, so the side that has more pressure is going to be most affected here. This side has 2 moles of B, 1 mole of A, so a total of 3 moles of gas on the left, only 1 mole of gas on the right, so there's more pressure on this side. So if I decrease that, it's just like we did up here with decreasing B. I'm decreasing a reactant, essentially, so it's going to shift to the left. Finally, if I increase C, if I increase the amount of a product, this was similar to increasing temperature, it's also going to shift to the left. All right, and you can try those practice problems in the video on Edpuzzle. I hope you enjoyed this. I hope it was helpful. Enjoy the rest of your day.